Uh, Lesson 5 deals with the limiting access reactants and some chemical analysis. So we'll start first with limiting access reactants. And we dealt in one of the examples, we dealt with that concept, but today we will see it even in more details. There are problems in chemistry that you will have to define the number of moles that are participating in the reaction. And some of the reaction are excess some of the compounds are excess and some are limited. So when they are excess, that means that when the reaction is completed, then some of the material, some of the compound is not participating in the reaction. And when it is a limiting reactant, then that means that reactant or that compound is fully used into a reaction. So in order to identify the problems where we can determine the number of moles, of each of the reactant, we will need to determine the limiting reactant and then use stoic. I will show you two ways that you can do this. Let's see this example here. When we have 39.0 grams of zinc are placed in 200 milliliters of 2.50 moles per liter silver nitrate, calculate the mass of silver formed. So as the very first thing, and everything that we have done even every time pretty much, is we write a balanced chemical reaction. So in this case, what we will have is a zinc solid is reacting with silver nitrate to form zinc nitrate and silver. We've seen this reaction even before. So now, the second step is to determine the initial moles of the reactant. So for the mass that we have given, because see what is given here. So we have a mass of 39.0 grams of zinc that is reacting with 250 milliliters at a concentration of 2.50 moles per liter of silver nitrate. And we are looking for the mass of silver formed. Okay, so everything in the reactant part is given, and this is the clue. When all the information in both reactant is given, both on all the reactant side is given, then you are dealing with limiting reacting or excess reactant question. So put that as a note. When all information needed for the reactant, both products, both reactants is given, then you are dealing with limiting reactant and excess reactant question. And you can solve it in one of the two methods that I will show you today. So when we have this, then as a second step, let's identify the initial moles of the reactants. Both of them. So for moles of zinc, what do we have is 39.0 grams of zinc. When we are using, when we have the grams and we want to find the moles, then we use the molar mass. So 1 mole of zinc is 65.41 grams of zinc. So grams of zinc and grams of zinc is cancelled out, and then what we have here is 0.596. Now, moles of silver, let's use a different one. Moles of silver nitrate will be the concentration, 2.50 moles of silver nitrate over 1 liter times, this is in 250 milliliters, which is 0.250 liters over 1. So liters and liters is cancelled out, and then what do we have here is 0.625 moles of silver nitrate. So now let's determine the limiting reactant. And the way that we do that is by finding the moles that are participating into the reaction. So now we have the moles of zinc as 5.9, whatever, and then the moles and the coefficient near zinc is 1. So then, therefore, the moles of zinc are 0.596 divided by the coefficient that is 1, so it's 0.596. And when we are talking about the moles of aluminum, silver nitrate, then the coefficient near silver nitrate is 2, so will be 0.625 divided by 2, which is 0.3, what is it? 0.3.625 divided by 2 is 313, let's say. So the number of moles of aluminum nitrate is smaller, therefore, the aluminum nitrate is the limiting reactant. And now, using the stoic, the unknown, we will determine now. We will determine which one, like how much precipitate is formed using stoic, but with the aluminum nitrate as the limiting reaction, because what it means that aluminum nitrate is ending up earlier than it's eaten up by the reaction, is used up in the reaction before zinc. So now we will use a stoic, so using the aluminum nitrate. So then we have 0.250 liters of silver nitrate, and using the molar or the concentration, 1 liter of silver nitrate is 2.50 moles of silver nitrate. So liters and liters is cancelled out. We are with moles of silver nitrate. Now what we will do is we will use the molar ratio of silver nitrate and silver. So will be 2 moles of silver nitrate and 2 moles of silver. So moles of silver nitrate and moles of silver nitrate is cancelled out. And then we will use the molar mass of silver. So 1 mole of silver. And on the numerator, we will have 107.87 grams of silver. So moles of silver is cancelled out, and we are ending up with 67.4 grams of silver produced. Let's take a look now to those examples, and I will show you a different method that you can use to define the mass of a precipitate or the mass of the product, as well as which one is limiting and which one is excess reactant. When we are not using the moles as you saw it here, but what we are doing is we are doing stoic, and then based on the information that is coming, then we decide which one is the limiting and excess reactant. So now we have 2.51 grams of sodium metal reacts with 9.59 grams of beryllium chloride. So the balanced equation is sodium plus beryllium chloride will give us sodium chloride and beryllium. So now we are determining for each of those problems which one is the limiting, is sodium or is beryllium chloride. So the information given here is sodium is 2.51 grams and beryllium is 9.59 grams. Now, you can pick any of the products here with my method, okay? But let's do the first method first. So we said that we will identify the moles of each. So moles of sodium we'll do stoic. So 2.51 grams. The molar mass of sodium is 22.99 grams. So grams of sodium and grams of sodium is cancelled out. And we have 0.109, okay, moles. And the coefficient nearby is 2, so let's divide this by 2, and we will have the moles of sodium participating in the reaction is 0.0542. And for the moles of beryllium chloride, we will use again stoic 9.59 grams of beryllium chloride times the molar mass of beryllium chloride, which is 79.91. So grams of beryllium chloride is cancelled out, and then what we will have is 0.120, and this is divided by the coefficient, which is 1, and will be 0.120. Since this number is 0.0542 is less than 0.1, then sodium is limiting reactant and beryllium chloride is excess reactant. Okay. Now the second method, or the method that I do, is that I do the stoic. So I start with sodium and I pick, let's say, sodium chloride or or beryllium, whatever in the product, and I go, how much is produced when all sodium is reacting, and how much beryllium is produced, or if you are taking sodium chloride, then how much sodium chloride is produced, and then you will have a mass there produced, and then what I do is I say, okay, what is the beryllium or sodium chloride, whichever you picked, is produced when 5.9059 grams of beryllium chloride is reacting in the reaction, and then I compare whatever is the lowest one is the amount that is produced, and whatever you started with is a B, is the limiting reactant. Therefore, the other one is excess reactant. So this one here, moles of what we have is methane is combusted with 28 liters of oxygen at STP conditions. So the reaction is CH4 plus oxygen is carbon dioxide and water. To water. Yeah. So now, when we have moles of methane, methane is 10.3 grams. So 10.3 grams of methane using the molar mass. We'll have 1 mole of methane is 16.05 grams of methane. So grams and grams is cancelled out, and then we have 0.642. This is divided by the coefficient of 1 that is near at methane, and we have 0.642 as the moles participating in the reaction, or that those grams of methane are converted to. And then we go moles of oxygen. We are dealing with STP conditions. So what we have is starting with what is given, 28 liters of oxygen. Molar volume is 1 mole of oxygen is 22.4 liters of oxygen. So liters is cancelled out, and then we have 1.25 moles divided by the coefficient of 2 that oxygen has will be 0.625. Since 0.625 is less than 0.642, then oxygen is the limiting reactant, while the methane is excess reactant. And when you have just this, like just this, to define which one is limiting and which one is the excess, this method is very fast. So now, 15 liters of 0.595 molarity of silver nitrate is combined with 25 milliliters of this to form whatever, to form silver sulfate and sodium nitrate. So the reaction that is balanced reaction is silver nitrate as sodium sulfate is producing silver sulfate and sodium nitrate. Okay. So now the information that we have here as silver nitrate is 15 liters with a concentration of 0.595. And then we have 25 milliliters with a concentration of 0.487. So as you see here, all the information in the reactant part is given. And this is, as I said, mentioned at the beginning of this lesson, this is the clue that you are dealing with limiting and excess reaction, the reactants. So let's identify the moles of silver nitrate. We'll start with what is given. So 15 liters of silver nitrate using the concentration 1 liter of silver nitrate is 0.595 moles of silver nitrate. So then we will have 8.93 moles of silver nitrate divided by the coefficient of 2, and we will have 4.46 moles of silver nitrate. Next one is identifying the moles of sodium sulfate, not nitrate, sodium sulfate. So we'll start with what is given, 0.0225 liters of sodium sulfate using the concentration 1 liter of sodium sulfate is 0.487 moles of sodium sulfate. So liters and liters is cancelled out, and we will have 0.0122, and this is divided by 1, that is the coefficient, so 0.0122. The moles of sodium sulfate is way lower than the moles of silver nitrate, so this is the limiting reactant, while silver nitrate is excess reactant. Okay, so now it is your turn to see what like 0.500 kilograms of potassium chloride reacts with 506 liters of oxygen at SATP condition, and determine the mass of potassium chloride that is it is produced. I will write the equation plus oxygen gas, it's producing potassium chlorate. Okay, so now determine the mass. We are determining the mass of the product. Okay, so now, you know what, I will do this. What is given here is 0.500 kilograms, which is the same as saying 500 grams of potassium chlorate, and the volume of oxygen is 506 liters at SATP conditions. Okay, so if we are doing it in the way that I have done it up to now, what we will do is we will identify the moles of potassium chloride, and then the moles of oxygen, and then see which one is limiting reactant, and then we will see which pick that and do stoic. And this is where I suggest you to do stoic with both reactants to see how much is produced. And this will be a different method on identifying both the limiting reactant and the mass that is produced. So on the case when we are using the method that I just explained to you, and I've been doing it, what we will do is we will identify the moles of potassium chloride. So we'll go 500 grams of potassium chloride times the molar mass of potassium chloride, which is 74.55 grams of potassium chloride. So grams of potassium chloride is simplified, and we will have 6.71 moles of potassium chloride, and divided this by the coefficient of 2 that we have in front of the potassium chloride, this will be 3.36 moles that this amount is translated on. And then we move to moles of oxygen at SATP conditions. So we start with 506 liters of oxygen times, using the molar volume, that is 24.8 liters of oxygen in 1 mole of oxygen. So liters is cancelled out, and then we will have 20.4 moles of oxygen, and this is divided by 3, that is the coefficient, and will be 6.80 moles translated. So therefore, this is the limiting reactant, and this is oxygen is the excess reactant. Now, in order to figure out how much is produced as a potassium chloride, then what we will do is we will use the limiting reactant. So we will do stoic with the limiting reactant. So we'll start 500 grams of potassium chloride times the molar mass, 1 mole of potassium chloride over 74.55 grams of potassium chloride. This will give us the moles of potassium chloride. Now we are moving from moles of potassium chloride to moles of potassium chlorate. So it will be 2 moles of, they are 2 to 2 moles, so the ratio. 2 moles of KClO3. So moles of potassium chloride is cancelled out. Now using the molar mass, that is 122.55, 1 mole of potassium chloride, 3, is 122.55 grams of potassium chloride. So moles of potassium chloride is cancelled out, and we have grams. So it will be 822 grams of potassium chloride produced. Now, what I suggest on this case, I will open a new page, and then what I suggest on a question when they're asking you, giving you everything in the reactant, and they're asking you how much is produced, I think that the best way to do is to do stoic for both of them. So what do you have as the balanced reaction is 2 KCl plus 3 O2 will be KClO3. Okay, so as a given here is 0.500 kilograms or 500 grams, and then we have 506 liters at SATP conditions, and we are looking for grams of this. Okay, so now what I suggest is do stoic for both of them, once for potassium chloride and potassium chlorate, and then for oxygen and potassium chlorate. And then you see which one is less. The one that is less is the one that is produced, and the one that you started with is the limiting reactant. So I will start with KCl first, okay, and then I will go 500 grams of KCl times molar mass, so that is 74.55 grams of KCl. So grams and grams is cancelled out. 1 mole of KCl. And now that we have the moles of given, let's move to the moles of asking, or the unknown. So 2 moles of KCl will be 1 mole of KClO3. So moles of KCl is cancelled out, and then we have molar mass of KCl2. So will be 1 mole of KClO3, and it is 122.55 grams of KClO3. So moles of KClO3 is cancelled out, and you will have 822 kilograms of KClO3. And then what I said is that you use oxygen now. So you start 506 liters of oxygen times molar volume at SATP conditions. So that is 24.8 liters of oxygen, 1 mole of oxygen. So liters of oxygen is cancelled out. And then you will use the molar ratio. So 3 moles of oxygen is 1 mole of KClO3. And then you will use the molar ratio, the molar mass as 1 mole of KClO3 is 122.55 grams of KClO3. And then in terms of the calculations, what you will have is 506 times 122.55 divide by 24.8 times 3, the whole thing. So you will have as a production of 833 grams, not kilograms. Even this one here is grams of KClO3. So as you see here, this is more. So then this is excess reactant, making this limiting reactant, and what the amount, the true amount of production is this one here. I hope that this makes sense. When the precipitate has settled enough so that the top layers is clear. Okay, so when you will see that the precipitate is completed when the top layers are clear and there is no cloud on it. Okay, if cloudness form, more excess reactant is required. If cloudness is formed, more excess reactant is required. And when there is no cloudness, form, then the limiting reactant is completed, is done. Okay. This is something that you can try it on your own, and if you have any question, then we can do it on in class. Okay, so you can do it any method that you want to, but I will say A and B with the second method that I showed you when you do stoic for both, in this case, NH3 and oxygen for the NO, like nitrogen monoxide, then you will do the stoich, and you will be able to answer both A and B. And then if you see that how much access is remaining after the reaction, then you can do that. You can try this on your own. Now let's move to the chemical analysis, where we will see how can we, or what are the three main methods that are used in a chemical analysis, and stoich is one of them. So there are three methods, three ways that we can work, or we can do, like, perform chemical analysis. The first one is gravimetric analysis using stoich. Using stoich. And what is happening is we are measuring the mass at the end. We are figuring out what is the mass, titration. Analysis, what we have been doing in the previous lesson. And again, what we are doing here is we are using stoich, and what we are finding from a measured solution volume. So what we are measuring the volume, and we are doing, we are finding the concentration. And then the other one is colorimetry, in which we are using the color of a solution and or flame test. Colorimetry flame test is conducted to determine the metal, determine the unknown metal or metal ion. For example, when you can use page 6 of your data booklet to determine a metal that is burning yellowish red, and this is qualitatively, we can determine the type of ionic species dissolved in a solution by using the information on page 11. So let's see an example. 1.0 molarity solution of iron 3 would be orange yellow. And a 0.0110 molarity of solution 3 will be pale yellow. So take a look on those pages on your data booklet, page 11 and page 6, and this will make sense. Okay, this concludes lesson 5, and we are pretty much done. Now we have a review, which we will do it in class.